So, hi everyone, my name is Zhengxiang Yi from Civil and Environmental Engineering. Today I'm going to introduce my final project of time series analysis, mostly number of earthquakes. So first of all, I'll introduce a little bit about the background and motivation of my study. There were two major earthquakes happened in last July in Ridgecrest, which were magnitude 7.1 and 6.4. I think most of you have a strong feeling about that. And those two earthquakes have triggered a widespread panic on the future earthquakes, especially in the Great LA area, since there are two major ruptures directly going through the city of LA. So people are really worried about there might be a very severe earthquake happen like 100 years ago. And another thing I want to figure out is whether the earthquake is predictable, or at least whether there will be some pattern existing in the number of earthquakes happen in the future. To explain these two questions, it can help to warn the public to get well prepared before the next severe earthquake happens. Also, it would inform the research community. For example, for the seismologists, they may have a better understanding on the earthquake mechanism. And for the earthquake engineers, they can get better prepared in terms of how retrofitting the building and doing some makes our city more resilient to get well prepared before the next earthquake. Then I'll introduce my dataset. So my original data is required from US Geological Survey, containing all of the detailed information, for example, the time, the magnitude, the source of the recorded that are greater than magnitude 5 earthquakes from the year of 1965 to the year of 2016. And on the right-hand side, it shows a plot of all of the special distributions of all of the recorded earthquake events. And the raw data just a single records of each earthquake. So to study the trend of earthquake activities, I count the monthly number of earthquakes from the original data. And on the left bottom plot, it shows the raw time series of monthly number of earthquakes from January 1965 to December 2016. On average, there are 37.5 earthquakes happen in a month. And as we can observe, after the year of 2000, there are three major peaks that after the year of 2000. And the most month is March 2011, when 228 earthquakes happened in that month. Like I said before, after the year of 2000, there are some peaks happen, so there might be some slight increasing trend. After this, I did a moving average, which makes the increasing trend is easier to be observed. Since there is a trend existing in the data, so the next thing I did is data cleaning. There are a couple of observations I can find from the original data. The first is there are some peaks after the year of 2000, which means the original data shows some time-dependent variance. To rescale the original data, I first took the logarithm of the raw data, which is shown in the right-hand side. And there are also some increasing trend can be observed. So I did a linear regression detrending to see whether this trend is significant or not. And the table on the bottom left shows the estimation of the intercept and the slope. And from the p-value, the slope is statistically significant, which means current era has more earthquakes happen than the previous era. There could be multiple reasons contribute to this fact. For example, we do have more significant number of earthquakes happen, and the earthquake activities is more intensive than before. There might be other facts contribute to this observation. For example, we may have more sophisticated measurements to record the earthquake, which would lead to an increase in the number of monthly recorded earthquake. We won't discuss the detailed reason contribute to this observation. And on the bottom right plot, it shows the detrended data. And this will be used as the raw data for the following analysis. So after getting the logarithm of the detrended logarithm of data, I first did a ACF and PACF to check which kind of model is more suitable to feeding the original data. As we can observe from the ACF and PACF, there are no obvious repetitive pattern can be observed. And also both ACF and PACF tail off, suggesting a remote model could be a good fit. And then I use both non-seasonal and seasonal model to model the detrended logarithm data. So on the left-hand side is a Bass ARIMA model 311, selected by the lowest AIC. And the detailed model is shown in this equation. It is interesting that the monthly number of earthquakes happen in this month, in the current month, is positively correlated to the last month, but negatively correlated to the previous 3 months. This might be kind of anti-intuition to some seismologists, because generally, if we have a month that of great number of earthquakes happen, we may think there are a lot of energy has been dissipated in the plate. So there may be lower number of earthquakes happen in the following months. But actually it is positively correlated. And on the left bottom plot, it shows the diagnostics of the residual. From the normal QQ plots, the residuals are almost follow the Gaussian distribution, and there are a couple of outliers can be detected, which corresponding to some peaks after the year of 2000. And from the testing statistics and the ACF of the residual, we can say that all of the residuals are independent. And on the right-hand side, it is a best seasonal ARIMA model 212100. And from the residual diagnostics, all of the residuals almost follow a normal distribution. And it's quite similar to what we have of the non-seasonal model. Almost no significant differences can be observed between both models. So in the following parts, I use both of the models to forecasting. So the data from January 1965 to December 2011 is used for training data to predict the data from January 2012 to December 2016. And the red line is a training prediction, and the blue line is the testing prediction. As we can observe, comparing the two plots, the training predictions are quite similar for the non-seasonal and seasonal model. Basically, both training predictions can capture the trend, but it cannot capture the variation. In terms of the forecasting, both models reveal very poor forecasting abilities. So at the first couple months, there are some fluctuations, and the seasonal model has more significant fluctuations than the non-seasonal model. After the first 5 to 6 months, all of the prediction deteriorate to a constant. So from the observation of the residual diagnostics and the forecasting, we may say that the detrended logarithm of data, it performs quite similar to a random walk, which means we cannot have a very good prediction on it. So maybe the earthquake activity is not predictable, at least by time. And the last, I did a spectrum analysis. On the right-hand side shows the non-parametric spectrum analysis results. There are 3 major peaks revealed in the raw periodogram. So the peak we are most interested in is the third peak, which corresponding to the months of 12.5 months. Since So first I smooth the parallelogram using a Daniel kernel, and after smooth, I found that this peak almost disappeared. So I'm really curious whether this is a statistically significant peak uh, against other peaks or not. So I computed a 5% confidence interval corresponding to this 12.5 month cycle, which is 0.025 to 1.45. In terms of the lower bound, which is 0.025, is still quite low, since we can observe there are a lot of peaks are above 0.025, this magnitude. So from the confidence interval, we can conclude that this 12.5 months is not a cycle for our raw data. So we can conclude from the spectral analysis that the detrended log monthly number of earthquakes is not, there's no cyclical pattern can be observed from it. So the raw data is closely to a random walk, which further means the number of earthquakes is not predictable, at least by time. If we may want to have a better prediction, I may consider adding more features, for example, the activities of the plates, for example, the deformation or the stress measured in the plate. There may be lead to a better prediction, just depending on time. Okay, that would be all of my presentation of the project. Thank you.